talk about shifting the neuroplasmin to mitochondrial disease, please.
Hello, good afternoon. Thanks very much for giving me this opportunity to speak to this audience. So this slide, of course, doesn't need comment in this room. So introducing mitochondrial DNA as a Pandora box for human diseases. So this is one of the reasons we hear. The second reason we hear that diseases caused by mutation in mtDNA are not treatable right now. So we're only limited to some supplement intervention exercise in some cases, and it's great to hear, or at least to watch how colleagues who are here trying to develop both pharmaceutical intervention or trying to prevent mitochondrial DNA disease by embryo manipulation, and also some genetic therapy interventions. And obviously, currently we're not able to manipulate mitochondrial DNA. We're not able to deliver healthy copies of the molecule to organelles. Therefore, if we think about genetic therapy or manipulating mitochondrial genome, we have to use some alternative approaches. And before I go and talk about the approaches we decided to take, just two recap slides about molecular genetics of mitochondria in order to set us for this talk in a correct way. So obviously, if we talk about mtDNA mutations, we need to talk about heteroplasmy and homoplasmy. And there is a threshold effect. So the mutation must reach certain level in order to time to manifestate. So on this scale bar, I'm trying to show that where we have a high load of mtDNA mutation, the function of mitochondria is compromised, indicated by the red color, and then with lower loads, the organelle is healthy. And the other important point for this talk is that mutant mtDNA is in majority of cases is functionally recessive. The other point I want to make is that cells keep mtDNA copy number constant. So if we take a cell and torture it a little bit by giving a drug that reduces copy number, and copy number is reduced, let's say, down to 10%. Once we remove this drug, copy number comes back again to the normal levels. We still don't know what's the mechanism behind it, but this is what happens. So the idea to use these features as in a therapeutic approach would be that if we take a cell with mitochondria with high heteroplasmy level and would be able to deplete only the mutant mitochondrial DNA, this is obviously will be correlated with loss of copy number, but selective elimination of the mutants and further recovery should result in recovery of in copy number of the healthy molecules, wild-type molecules, therefore restoration of mitochondrial and cellular function. And this sort of approach has been pioneered about 15 years ago by a group of Carlos Morales in Miami. And what he did, he targeted to mitochondria a restriction enzyme. So it's a naturally occurring enzyme, a nucleolytic enzyme, meaning that it's able to cut DNA. And if you attach a mitochondrial targeting sequence, this protein can get into the organelle. And because these nucleases are very specific, if we have two different haplotypes and only in one of the molecules there is a recognition site for this restriction enzyme, as we call it, this molecule will be deleted. This is happening because any double-strand break in DNA results in very rapid depletion of mitochondria. And this was followed up a year after in more disease-relevant settings, where a group from Japan targeted an enzyme called SMA1, which recognizes the following sequence, CCGG. And this sequence it can be generated by mutation which is responsible for the NAR disease, and I'll be talking about this disease a little bit more further on. Unfortunately, not every mutation will result in generation of restriction site. Therefore, this approach is not universal by definition. However, currently, we are able to design proteins that can be selected to bind almost any DNA sequence. And one type of these proteins are called zinc finger. So zinc finger, the name comes from the fact that this fold looks like a finger, and there is a zinc ion which is chelated by cysteines and histidines from the structure of this protein. And this single finger recognizes 3 base pairs of DNA. Then you could, because of this modular structure of zinc fingers, you could link several fingers together and have a specificity to the longer sequence of DNA. And also currently, by manipulating the sequence of these proteins in so-called contact amino acids, we are able to design artificial zinc fingers that can bind to any predetermined sequence. And so this approach can be used in several different scenarios. For example, we could design a zinc finger that binds in promoter of a gene and attach activation domain or repression domain in order to intervene with transcription of the gene. We could also attach a methylase domain and then introduce methyl group site in a site-specific manner, so where we want in the molecule. And what is the most interesting for us is that we can attach a nuclease domain, so a domain that can cut DNA specifically. So in more details, how this design looks like, we need to have 2 zinc fingers binding on the opposite strands, and then we have a nuclease domain from FOC1 restriction enzyme. That is a special type of restriction enzyme. I don't want to go into the details. And then, if these 2 reagents dimerize, come together in this site, a double-strand break is produced here. So we wanted to exploit this architecture, and we asked whether it's possible to target these zinc finger nucleases into mitochondria, and whether they will be able to recognize DNA sequence specifically. So as a model sequence, we decided to use the NARC mutation in position 8993. It's D2G mutation. It's the same mutation that was used in the case of the SMA1 restriction enzyme I just alluded to. And so in this scenario, in the healthy molecules, the zinc finger nuclease doesn't bind. Only one of these monomers binds, but this is not enough to create a double-strand break. Whereas in the mutant scenario, both of these reagents bind to DNA and create pigment. So it's probably easier to say than do. It took us many years to develop an efficient reagent, but this is more or less how our latest design looked like. So we have the mitochondrial targeting sequence for each of the monomers. We have a short sequence that allows for recognition of this, of each of the monomers, the different so-called epitope tags. And then nuclear export signal. This is necessary for efficient targeting of these molecules into the mitochondria. Then we have a specific zinc finger peptide that binds, in this case, the NARC mutation, and also a nuclease domain that has been engineered in a way that we cannot create homo dimers. It means that red monomer cannot pair with red one, and blue cannot pair with blue one. It's been achieved by mutating 6 residues in the structure of the FOC1 nucleolytic domain. So, having achieved this architecture, we went into experimentation. So, in one of the first experiments, we taken cycle cells with very high loads of the NARC mutation. It was about 93% of the NARC mutation. And in this cell line, we expressed either one monomer individually, so the red or the blue individually, or both of them together. And then when we analyzed the mutation load by a technique called last cycle PCR, so we perform PCR and then add radioactivity to the last cycle, and then we use the same restriction enzyme that has been introduced a couple of slides ago in order to cut and distinguish between the mutant and wild-type mitochondrial DNA. So as you can appreciate from panel C here, we got a significant shift towards the wild-type in these cell lines. What is also important that in this experiment, zinc finger nucleases were expressed for a very long time. And so as you can see in the control samples here, within this time, actually the mutant load even went even further, so to about 97% mutant. So what we are doing here, we are shifting the heteroplasmy towards the wild type at least five times. But we wanted to improve this system because the long-term expression is probably not great for cell, and also we thought that we don't need it. We just want to change heteroplasmy, allow the cell to repopulate, and then hoping for that the function will be restored. So to do that, we've taken a different approach. In this case, we now expressed our monomers, but on the same vector and the same piece of DNA that encodes these monomers, we have a fluorescent protein. So in the case of the mutant specific monomer, we have a red fluorescent protein. In the case of the so-called companion zinc finger nuclease, we have a green protein. So then this allows us to sort cells that express or co-express both of these variants at the same time. So these are some samples of this analysis. Basically what we do, we co-express these two vectors together and ask the machine to sort the cells which are here. We call them yellow, because that's quite often it's what you result by overlaying green and red in this sort of experiment. So what we observe here, that after co-expressing both of these molecules, we see a substantial shift in heteroplasmy. Now we are using a different cell line that has more wild-type molecules. It's probably easier to shift this cell line as well. But we could see a shift in one experiment. We could shift from about 20% to about 50%. What you can also appreciate from panel B here, we see a substantial depletion in the copy number, in the mtDNA copy number, and I'll come to this later on. What is also important that if we take two zinc finger nucleases that are not related to mitochondrial DNA at all, they don't shift the heteroplasmy. However, they still deplete mitochondrial DNA. So then, when we analyze these cells after 2 weeks or 4 weeks, we could see gradual recovery in mtDNA copy number. So after 14 days, we have about 52% of the initial numbers, but after 4 weeks, after 28 days, we see a full recovery in the copy number. But obviously, there's one more thing I want to tell you this. So what happens if we take cell line from the first experiment and deliver zinc finger nucleases to the cell line again, perform the fluorescent activated cell sorting FACS, and then reanalyze these cells. This is what we did in this experiment. They underwent 4 rounds of transfection and recovery, and as you can see here on this plot, we starting from 20% of wild type, we could recover 93% of the wild type mitochondrial DNA. And when we analyze these cells after recovery period of 28 days, they always fully recover mitochondrial copy number. And what is also important, the function of mitochondria is recovered as well. We were not able to do this sort of analysis, respiration analysis, in the previous experiments because the shift was not enough. However, with this sequential delivery and recovery, we are able to see a phenotypic change as well. Okay, so let me come back to these results about the mtDNA depletion. We hypothesized that this is the result of very high expression of our zinc fingers. Therefore, in this experiment, we sorted 2 populations of cells expressing zinc finger nucleases. So in the first, in this purple, that we call gate, we sorted cells that are not so bright in terms of in terms of the expression of the fluorescent protein markers, and so this should be correlated with lower expression of zinc finger nucleases as well. And we sort the bright population, which is supposed to have high expression number. And then when we analyze the expression levels of this protein, you can appreciate that there is a difference between these 2 populations of cells. And so what we see here is that when we use a so-called dim cells, so the ones that express zinc finger on the lower level, the actual shift in heteroplasmy is greater as compared to the bright cells, so the ones that overexpress on the very high level. What is also important that after 18 days, the dim cells, the lower expressors, recover mtDNA quickly. And actually, when we did it properly 3 times, we discovered that only the low expression level molecules, they shift heteroplasmy, whereas the high expressors are counterproductive. So it's probably, you could compare it by the star activity of restriction enzyme for those who do DNA cloning. So in this case, less is more. It's probably due to a specificity of these reagents. It's simply a dosage effect. We cannot overdose these things. However, in more medically oriented applications, sorting cells, it's only what we did is only experimental thing. We cannot sort cells in patients. So we are playing with, we're designing and devising ways of lowering expression of the zinc fingers. And in this case, what we use it's an element that regulates expression on RNA level, called hammerhead ribosome. So it's what we added here is a piece of RNA which self-cleaves itself. So in the mRNA for this nuclease is cleaved constantly, unless this hammerhead ribosome has been engineered in a way that if you add tetracycline, which is well known and used and approved drug, if you add tetracycline, this cleavage reaction is not longer, it doesn't occur any longer. Therefore, we have a system where we could titrate the expression of these molecules using tetracycline. And also, this is a universal system, so we don't rely on using different promoters. We could use relatively strong and constitutive promoters in this case. So this is just an example of how a comparison of expression of zinc fingers without the hammerhead element, and if we compare it with the now with the self-cleavage reagent, it's only about 10% of the initial one. When we add tetracycline, the expression level rises. So now we tested that and again in the same experiment. We deliver both of the monomers, and that's the full expression, which the shift is as before, more or less up to 40%. However, when we lower the expression, within single experiment, we could achieve shift up to 80% of the wild value. So this is confirming our previous results with the fact score. Okay, so this is where we are with the design. I'll talk about further steps a little bit later. So the other mutations, the other mutations in mtDNA that cause, as we heard a moment ago, that 15% of all mitochondrial diseases are large-scale rearrangements. One of these large-scale rearrangements occurs between ADP8 and ND5 genes, and it's so-called common deletion. It's been described by Massimo and Billy DiMauro in the early 90s. And this is a quite common single deletion. So we wanted to see if it's possible to target this sort of rearrangement as well. So in this scenario, we designed two zinc finger monomers that bind on the opposite side of this deletion. So in the wild-type molecules, the two monomers are far apart, so they cannot dimerize, therefore they cannot produce double-strand breaks. However, in the mutant, in the common deletion mtDNA, they come together and should produce the cut. And this is an example of experiment where that proves that this approach is working. We again deliver single zinc finger nuclease, so the left-hand side, right-hand side, and both of them together. They are nicely expressed in these cells. And we use the cell that has only about 16% of wild-type DNA. However, treatment of this cell line with both of the monomers shifts heteroplasm to about 70, 75, 76, 76%. So again, this approach is quite universal, and we could use it for large-scale deletions as well. And this is just a quick slide to show that the function of these cells are fully recovered as well. So the blue traces here is the respiration of the cell before treatment, whereas the greenish traces are respiration of cells after treatment. And also, when we measure the steady-state levels of the respiratory chain complexes, they also recover to the level of wild type. Okay, so this is where we are with both point mutation and large-scale deletions. And we are not the only people doing this sort of work. You might be aware that there is another type of DNA-specific proteins that can be engineered to bind new sequences. They are called tails. And if you link these proteins with a restriction enzyme in nuclease, you could create a tail nuclease and abbreviated as TALEN. And so there are some recent reports about very successful use of talents in mitochondria. They're called mitotalents, surprise, surprise. And then, so what Carlos Morales and his group did in this study was to target one of the lone mutations and also common deletion with very similar results to ours. Very recently, talents were used to shift heteroplasm in the mouse oocytes in a model that contains two different haplotypes. This is not a disease-related model. However, what the same study has done, they also shift heteroplasmy of human mutations by creating a chimeric mouse and human oocytes and deliver mitotalents to this. So both of these studies are very convincing and elegant. So we also at some point to give a go to talents. We created talents to the same NAR 8993T mutation. However, at least in our hands, we are not able to shift heteroplasmy efficiently in this cell. So as you can see from this slide, we use several different designs. However, at least in our hands, these reagents are not efficient. So it might happen that talents will be better for some mutation, whereas zinc finger nucleases might be better for some other mutation. It might have to do with the composition of the binding site. Okay, so that's the conclusions for now. So zinc finger nuclease can be successfully delivered to mitochondria by capable of selectively eliminating pathogenic MTBR. Multiple treatments can produce greater shifts, and dosage is very important while using these molecules. And also, if we treat with zinc fingers, we can alleviate the oxphos phenotype. So I have 3 more slides about future direction. What we're planning to do now, we want to use this zinc finger approach in gene therapy in mouse models, both in somatic cells therapy, also using in germline and embryo type cells. And also there are some plans in using zinc finger nucleases to heteroplasmy in human embryos and oocytes. And I just briefly, we are lucky enough to collaborate with groups in Cologne. And this is a long story how this mouse model is developed, but we have to be aware that not many mouse models of mtDNA disease. So this is very precious model. But Niels Goller-Larsson and James Stewart are very open and share this model with us. So in this scenario, this is a mutation in tRNA alanine, and it produces a muscle phenotype, to cut the long story short. So we were very busy in testing several combinations of zinc fingers that would specifically bind this mutation with an intent of delivering into this animal. So this is a fragment of my text conversation with a postdoc, and basically that's the summary of what we got now. He said that it worked from 28% of this tRNA alanine mutation. We are able to shift to 50 in one experiment. And he also was very happy, but I had to blank this word here because it's not very appropriate for the audience. So in more scientific terms, what have we done? We again used the 2 monomers that were co-expressed with fluorescent proteins. We transfected mouse embryonic fibroblasts having this mutation, sorted the 2 co-expression, and then analyzed their sequences. And this is where we are. So in low dosage, we are able to shift from about 30% to about 50%. And in a higher dosage, the shift is there as well, however, to a lesser extent. And so now we are ready to construct the AAV virus, and this is already on the pipeline. It's almost ready. And we are able to design a vector that contains all of the elements necessary for expression, also the hammerhead ribosome that reduces the expression and is inducible inducible by tetracycline into single AAV vector. I think it's an important achievement because if we compare it with talents with similar recognition length, so if you want to recognize 18 base pairs, this single monomer of talents would be 3 kb. So if we need 2 of them, they won't be able to fit into single AAV vector. So that might be another advantage of using zinc finger nucleases as opposed to talents. And with that, I'd like to acknowledge people involved in this work. So Payam was already acknowledged by sending me explicit text. Also other members of my group who helped with this experimentation. This work was pioneered when I was a postdoc in MRC LNP in Cambridge. I'd like to thank Massimo and Carlo for helping us with the mouse work. Also, we have a collaboration with Christian Freza. We're doing some metabolomics in the cell lines that are shifted. And also, very important, all zinc fingers were designed by Sangamo Biosciences, purely on scientific collaboration. We didn't pay for it. These reagents are usually quite expensive if you want to order them from the company. And also, Jean-Paul helped us to design talents, and James and Niels were mentioned to provide the mouse, and these people help us with fax sorting. So thanks very much.
Many thanks, Dr. Mitocon, for this very interesting therapeutic approach to treat mtDNA related disease. And discussion and the presentation is open for discussion.
In the sequential treatment with the zinc finger.
You want to jump?
Sequential treatment with the zinc fingers was a clear improvement also in the vector only treated cells in your slide.
So let's go to the audience.
The shift from 20 to 80, 70.
No,
Can you
it's
comment?
no. It's just because for each treatment you have to use control. So what we're doing here, we treat these cells and shift them to 42%, and we take the same cells and treat them with vector and zinc fingers. Yes.
Okay, from the 42 to
Yeah. So let's say if we take second treatment and go into the third treatment, we take a cell line that is already 70. We treat it with vector, nothing has changed here, and we treat it with zinc fingers and it has changed, and it's taken. So you need to control on each step. Okay, but it's a good. I don't really like the way this is presented right now. I have to think about a better way of presenting it. But it's an easy experiment. But
4 months of treatment from the first to the last. 1 month for each treatment. I don't know if the natural shift of.
This is quite stable. We don't see a shift if you don't apply.
So I think that this is a fantastic device. For the first time we have some tools to manipulate the controlled way mitochondrial DNA. I'd like to emphasize the importance of this line of research. Of course, the crucial, I think, two crucial important questions is: do you have a vector that can address and target critical organs in any efficient way, first? Second, what about the time lapse of the unavoidable mitochondrial depletion that the tissues will undergo under this treatment. Is this critical quantitatively and in terms of time?
Okay, so to answer your first question, in these mouse experiments, we're planning to use AAV 9.45, which has been shown to be not accumulating in the livers, but going to muscles quite easily. So, at least for the application in the mouse model, we do have a suitable vector, and this is done. In terms of taking this forward, I think it's in the group, we won't be able to sort out all the questions. So we're leaving it to specialists from gene delivery in order to decide what would be the best way of delivering these molecules into humans, for example. And your second question was depletion. Yes, that's why this is a very important issue. That's why we're playing with the dosage. And so I think, as for every drug, if you overdose, it's not healthy. So you have to be very careful and take the most selective reagents to only deplete the mutants, and also do this depletion in a very gentle way. So if you say 90% heteroplasmy, it probably is not the best idea to deplete it fully, because you end up with 10% and you generate mitochondrial depletions in you. So dosage would be very important for this sort of applications.
Okay, thanks a lot. And we move to